This PowerPoint is over electrostatics. Now the term electrostatics actually, electro is a word that means charge and statics is mean sitting still. So basically this is about charges that are sitting still. First of all, we're going to discuss the parts of the atom. We got three parts of the atom, major parts. You got two on the nucleus, two parts in the nucleus, and one on the outside in the cloud. And this object here is going to be a proton. This object here is going to be a neutron. That makes up the nucleus, and then we got the electrons that are going around the outside of the nucleus. Now the charges, proton is going to be positively charged, neutron is neutrally charged, and electron is negatively charged. And it's important to realize this before we start moving forward. Protons and neutrons that are in the nucleus, they're in the center of the atom. They're extremely hard to move, and for what we can do in a physics class, we can't really do anything. So it's essentially impossible to remove or add protons or neutrons to an atom. However, electrons can be removed or added fairly easily. As a matter of fact, just rubbing your hands together, you can exchange electrons from one thing to another. So in order to change the charge of an atom, we have to either add or take away electrons. That's the only way to do it. So we can't add or remove protons. We have to add or remove electrons. So to make something negatively charged, we're going to add on electrons. To make it positively charged, we're going to remove electrons. So in class we complete the electrostatics lab, and there's a few main points that I want you to know about the electrostatics lab before moving on. First off, an object that is charged is only charged because we either add or take away electrons. We can't move protons. Protons can't be added or subtracted, at least for what we can do in this class. So in order to charge something, you either have to add electrons, which makes it negatively charged, or we can take electrons away, which makes it positively charged. Now an object that is neutrally charged, the only reason it's neutrally charged is not because there are no charges whatsoever. It's because there are an equal number of positives and negatives there, and that's what makes it neutral. Now when I bring this negatively charged object close to this neutral object, then what happens is that the opposite charges will attract to the charged object, and the like charges in the neutral object will repel from the charged object. And what that does is that basically gives you two forces. That let's say that the charged object here is negative. So then the positives in the neutral object will attract towards it, and then the negatives will repel away. Now what that means is that we're going to have two forces that are going to be acting, but one of those forces is going to be stronger than the other, and that's because of the last point here. As distance between charges increases, the force will decrease. So as we said, the opposite charges will attract and they'll get closer, so that means the force of attraction is going to be stronger. And then the like charges will repel away, so that force is going to be weaker. And the reason a neutral object will actually attract toward a charged object is because that neutral object has its opposite charges that are closer to the charged object, and its like charges are further away, so the attraction is stronger than the repulsion. Now another way of charging something, we did in the lab, we did friction. We rubbed two objects together that transfer charge. Another way you can transfer charge is by contact. So if you have something that's already charged and you bring it close to something that's not charged, what that will do is when you put in contact these two objects, then that will transfer some of the charge over, because these electrons, they want to get as far away from each other as they possibly can. And then if you remove it, then that leaves a net charge on this other object. Now, another word for this is referred to as grounding. So you have a plane here that's attached to the ground, that wire that goes to it. And the reason that wire is there is so that electrons do not accumulate on this plane. Because if somebody wants to fuel the plane, you have fuel that's going through the fuel lines, which actually adds friction. And because that fuel is moving through the fuel lines, you get a transfer of charge by friction. So you could potentially have a buildup of charge. And if that charge builds up enough, it can actually cause a spark to transfer the charge to somewhere else, and therefore the fumes would ignite. So effectively what we do is we take the plane itself and we attach it to the biggest thing around, and that's the planet Earth, to allow the electrons to spread out as much as possible so we don't build up that charge. This is a Van de Graaff generator, and basically what this does is this rubber band that goes around has a positive charge because the electrons are being pulled off down here by the brush, and then it goes up to the top here, and then it pulls the electrons off this metal dome, and then those electrons come back down and lets those electrons go. So basically, it transfers the the negative charges off the dome here and transfers it to the ground here. And what that does is that leaves a large positive charge on the dome, that which when something comes close that is negatively charged or even neutrally charged, that charge will actually transfer over, and it'll make a big, essentially a big lightning bolt. And this is a demonstration that we do in class. Next thing we're going to talk about dipole. The term dipole, what it means is that basically, we could think of the paper that we had the demonstration before in the paper pickup. When the positive cone came close to it, the positives were pushed away while the negatives were pulled closer. Now the paper is still technically neutral, but the charges are shifted away from each other to where there's a positive end and a negative end. Well, water is actually naturally dipole. And this is a very important thing, especially for life on Earth, because what happens is water actually splits up the positives and negatives that are in things like salt, sodium, and chlorine, and then allows the electrons to move freely. And those electrons moving is what gives us our electrical impulses in our body to be able to function and move and think and do things like that. The reason water has a natural dipole is because it has two positives here that have the hydrogen and the oxygen right here that holds on to the electrons. Now there's a covalent bond between the oxygen and the hydrogens, and basically what covalent means, it means it shares the electrons, but the electrons don't equally go to both of these atoms. What they do is actually the negative charges that stay around the oxygen atom more often, and that's actually what this symbol means. It's a delta, it's a lowercase delta negative, meaning that the charge is mostly negative for the oxygen atom and then mostly positive for the hydrogen atom. And as that electron transfers back and forth, mostly staying around the negative, or I'm sorry, around the oxygen, you can kind of think of this as two parents that are divorced that are sharing a child. The mom may get the child 5 days a week on the weekdays, and then the dad gets the child on the weekends, but the mom has more custody of the child. That's the same thing here. The oxygen atom has the electron more often than the outside, so the outside hydrogen. So the positive charge over here and the negative charge over here creates a dipole. Electrically, it's all neutral. There's just as many positives and negatives inside this molecule, but it's shifted to where one side is positive and the other is negative. And basically what this does is this dipole nature, there's a demonstration I do in class where I have a charged rod that I put close to water, and the water will actually shift around to where that rod is negatively charged. The positive end will actually attract toward it and actually bend water. It's a pretty cool demonstration. So the electrostatic force is actually a field force, and what that means it's a force that acts over a distance as opposed to two objects that are touching each other. You don't have to have the charges touching each other in order for a force to be applied. That's the same as the law of gravity, and we're going to look at the law of gravity. If you remember from before, it's the force of gravity is going to be equal to the gravitational constant, which is 6.67 times 10 to the negative 11 times mass 1 times mass 2 divided by the distance between the two squared. And the reason I bring this up is because Coulomb's law looks very, very similar. We have the electrostatic force times Coulomb's constant here, which is 9 times 10 to the 9th newtons meters squared per Coulomb squared. Don't worry too much about the units here, just the 9 times 10 to the 9th. As long as everything in here is in base units, then there's not much to worry about with those units. And then we got two charges on top, charge 1 and charge 2. These two charges, the amount of charge affects how much electrostatic force there is between the two charges, and the more electrostatic force, the more charge, the more electrostatic force it's going to have. And it's measured in coulombs, and that's going to be a new unit for us for charge, a coulomb. And then we have the distance between the two objects, which is measured in meters. The force is going to be along the line of the two charges. So we got two charges that are either going to be attracting toward each other or they're going to be repelling away from each other. So we don't have any forces here that are going to be perpendicular. There's no force coming up here or down, which may seem kind of ridiculous, but there are some forces. The magnetic force, the electromagnetic force actually can be perpendicular with the charges, but we're not going to get into that right now. Basically, the force is in line with the two charges itself. Positive positive and negative will always be attractive, and repulsive forces for the positive, positive, and negative, negative. Now, if you think about the electrostatic force equation, the electrostatic force equation is charge 1 times charge 2. If we take this positive and multiply by a negative, we're going to get a negative force. And what that negative means attractive, because we know a positive and negative will always attract each other. If we think of two positive charges, positive times a positive will give us a positive force, which means repulsive. The negative times a negative will also give us a positive, which means it's going to be a repulsive force. So the electrostatic force equation will actually tell us whether it's going to be attractive or repulsive. Now, sometimes we don't really need to worry about that because we know positives are going to repel each other. We know a positive and negative is going to attract each other, so the negative we can kind of ignore. But the electrostatic force does actually tell us the direction of the force. Now, this direction is different than what we've dealt with before. The direction is either in, which is negative, or out, which is positive. And then we have to translate that over into the directions we're used to, which is going to be left and right. And we'll do that in some of the examples that we do in this PowerPoint. The inverse square law, this is true with gravitational force. It's also true with the electrostatic force. Basically what it means is the force decreases by the square of the distance. So if I have these two objects that have a force between them, if I double the distance, then what that's going to do is that's going to have 1/4 the force. Now think about that. Twice the distance, 2 times the distance, the inverse of that is going to be 1/2, and then 1/2 squared is going to be 1/4. So with twice the distance between the two objects, we're going to have 1/4 the force. That's the inverse square law. Now, the inverse square law tells us that when we increase distance between two electrostatic charges, the electrostatic force will decrease by the square of the distance. So let's do these examples. It says here that two charges have an electrostatic force of 100 newtons between them, and then the distance is doubled. What's going to happen to the force? What's the new force going to be? All right, so that 2 that we're going to multiply the distance by, that's really 2/1. So then if you do the inverse square, the inverse of 2/1 is 1/2. And then you take that 1/2 and you square it. And when you square a fraction, you square the numerator and you square the denominator. So it's going to be 1 squared divided by 2 squared, which gives you 1/4. So with twice the distance, with doubling the distance, you now have 1/4 of the force. So if the force was originally 100 newtons, we multiply that by 1/4, and we get our new force is now going to be 25 newtons. The next example says two charges have an electrostatic force of 50 newtons between them, and then we change the distance to 1/3. Now, the inverse square law says that if you decrease the distance, that'll increase the force. So we should get a force greater than 50 newtons. Let's see what we get. All right, so 1/3, the inverse square, so the inverse of 1/3 is 3. And then we take 3 and square it, and you get 9. So now my new force is going to be 9 times of what it was originally. So if it was originally 50 newtons, multiply that by 9, and we get that it's going to be now 450 newtons. So we do see an increase as the increase from 50 to 450 because the distance decreased. And the next example, it says two charges have an electrostatic force of 30 newtons between them. If the distance is 1/2, then what's the new force? So if we take that 1/2 and we take the inverse of that, we get 2. And then we take the square of 2 and we get 4. So now my new force is going to be 4 times of what it was originally. So 30 times 4, that gives me 120 newtons for my new force.